proceed further. So we have discussed about a specific algorithm called as decision tree. Within decision tree, we discussed about various techniques, but what is the name of the algorithm that we have spoken about? The name of the algorithm is greedy algorithm. And within greedy algorithm, you choose that variable which gives you the highest information. So how do you calculate the information gained or information available within each and every variable? What is the formula for that? Entropy before minus entropy after. And this will help us calculate information gain for each and every variable. And then how do you choose a root node? Root node is that node which has the highest information gain. Okay, highest information gain, that's called as your root node. Okay, what is the formula for entropy? I equal to 1 until n, probability into log of probability. This is very important formula. Very, very important formula. Don't, forget that, please. Okay. Now we need to get into ensemble methods. Okay. What are the regularization techniques within decision tree? Pruning, absolutely. Yeah, absolutely. Within pruning, you have pre-pruning and post-pruning. In the interviews, people might ask you which of the hyperparameters or which of the regularization techniques fall under pre-pruning and what are the other regularization techniques which would be part of post-pruning. And you should be in a position to answer this. Okay. So that's about the decision tree. Okay. And then we switch to ensemble techniques because we understood that when we use a single algorithm, each time you split the data into training and test, and when you build a model, right, results might vary. There has to be a mechanism to run the algorithms multiple times on different data sets and then combine the results. That would bring more stability into your algorithm. Okay? It will not give you different results altogether because you're taking an average. Okay. Next, we have homogeneous and heterogeneous ensemble techniques. Homogeneous means we use the same base learner. Base learner means same algorithm. And we also have heterogeneous. Heterogeneous means you use different set of algorithms. So homogeneous, heterogeneous. And we also have generative versus non-generative. Generative means the results of one algorithm would move on to the next algorithm. Boosting, bagging, random forest. And when it comes to non-generative, they just take the results of the algorithms and combine the results in some way. What are the techniques? Voting and stacking. Within voting, you can have hard voting or you can have soft voting. Soft voting is nothing but taking an average. And within average, you have simple average and weighted average. Good. So we understood all of these things. Now let's get into bagging and let's understand more on bagging. Okay. Even before that, let's talk about sampling or resampling. Let me see if I've made a note of this. If not, that is absolutely fine. Because I will anyways. when I think that option or those details are not recorded by me in a detailed manner. Having said that, that should not bother us at all. Okay, so that's fine. So friends, ideally, what is sampling? Sampling means you'll have population. From this population, you take a sample. Correct? Since we cannot work on complete population, we get the sample out. This is sampling, right? Basically. Because we cannot take the entire data and we will not be able to get access to the complete data, we get a sample by performing a simple random sampling. From this sample, so this is the data set which will be given to you by the customer, for example, or this is the data that you collect. You obviously cannot get access to the complete population. So what do? You get sample. And once you get sample, what do? You're going to once again take that sample and split the data into training and test. That process is called as resampling. Ideally, it is called as what? Resampling. Okay, when you apply this resampling technique, what do you get? Subsample. Means from this sample, you're trying to get a smaller portion, which is called as a subsample. Or think about this as your training data set on which you're going to train your model. All these subsamples, think about these as your training data sets on which you train your models. And there is something called as bootstrap sampling. Or bootstrapping. Okay. So what do you mean by bootstrap sampling? Sampling with replacement. So suppose you have a sample of some 1,000 observations or 10,000 observations. Okay, say in this data set, you have your output variable and input variables. When you try to randomly take a sample into your training data, and then remaining, if you want to put it in test data set, for instance, say you want 80% of data into training and 20% of data into test. Then for this training, suppose randomly row number 2 is selected from these 10,000. Now, when the next observation should be randomly sampled, do you know what? Again, you're going to randomly sample from all 10,000. 2 got selected does not mean 2 will be removed. 2 got selected, you put it here. For the next sample, again, randomly from these, you select. Say you randomly selected row number 100. You put that. You mention. Then again, when you sample, probably 2 get selected once again. Because you're sampling with replacement. Okay, we are sampling with replacement. In that way, you select. Bootstrap sampling is what we call this as. When you create n number of samples like this, meaning you have come up with the training and test split. Again, you come up with another training test split. Again, you come up with again training and test split. Different times if you split it in this way with the replacement. People say that there is a specific rule, which is roughly 36% of the observations will not be selected at all. Out of 10,000 observations, roughly 36% of the observations will never be selected. Okay, let me give you the exact number so that I don't end up giving you a wrong number here. Okay, 36.8 to be exact. This is what people have figured out by doing a lot of experiments. That means each observation has a probability of getting selected in the samples for what percentage of times? 63.2% of times. Okay. That means 36.8% of the original data set, okay, would always be out of bag. It won't be in your training. It will always be out of bag. It won't be in bag. In bag is also called as in sample. Out of bag is called as out of sample. Okay, so 63.2% will be the probability of these instances to be selected in training data. 36.8% is the probability of each instance that it will be out of training data. Out of training means it can be part of validation data or test data set from machine learning or predictive modeling standpoint. You can do this experiment and you'll very soon understand this. Okay, next. Bagging means bootstrap aggregating. B stands for bootstrap. Aggregate. AGGING is for aggregating. AGG is for aggregating. So how does it work when it comes to bagging? Bootstrap aggregating. Say you have a training data set. Okay, whenever we have data, we know for a fact that we need to split that data into training and test. So say you have output variable and input variables. You have some data, 10,000 observations. What do? You randomly split this data into training data set and test data set. Okay. Randomly we are doing this. Randomly we are splitting the data into training and test. And then what do? You build your model on the training data. This building the model is called as a base learner. The baseline model that we are building. Then once you build your model, what do? You test it on the test data. When you test it on the test data, There are multiple ways of combining the results. One is, do you want to combine the results of overall accuracy, or say 20% of 10,000 will be how many observations? 2,000 observations. Say observation number one, output is, will a person default or not? Say you have inputs. So the last one is not there. Say you have the inputs. When we give these three inputs to your base learner one, base learner one will give you some result that, okay, person will default. So base learner one is giving you an output that person will default. Keep the result like that. Now what happens here? Bootstrap sampling is going to happen. What do you mean by bootstrap sampling? Sample with replacement. So again, you split this data into training and test. And then build a model once again on this. When you build the model, you use base learner, another base learner that is called as base learner 2. Same decision tree. Here if you use decision tree, and here also if you use decision tree, etc., it will be called as homogeneous ensemble technique if you use the same set of algorithms. And then once again test it on the test data. When you test it on the test data, for this observation number one, maybe you get a different result altogether. Maybe base learner 2 might say that result is not default. Again, in that way, again split the data, and then you get base learner 3. Again, you test the data, you get base learner 4. But remember one thing, that the test data will remain the same. This will not change. Test data will remain the same always. First time you split right, training and test, you have the test data. The test data will remain as is. The only thing that will keep changing is your training data. Okay. Even when you split, forget about test. Only take train the model. Then test it on this test data only. Only then for every observation, you can test it using different algorithms, different base learners. Otherwise, if the test data is also different, then how would you look at predictions for this observation one? Within this first split, maybe in test data, you have this observation. In the other splits, you need not have this observation. This observation one might go into your training data. Hence, test data will remain as is. Your training data will keep on changing. And as in how you build the model, bring it and test it on this. Say base learner says that, 3 says that person will not default. Now you combine the results. How do I combine the results? What will be the final output for this? Not default, majority voting. Voting happens, hard voting happens, majority voting, right? You vote the majority. So the final output will be person will not default. Instead of this, if the output variable is salaries of people, then base learner 1, you split the data, you train the model, build your base learner 1, test it on the test data. For the person 1, it might so happen that salary will be 10 lakhs per annum. Then again split the data, take the training data, train your model, test it on this test data. Then say salary would be 900,000, 9 lakhs. This might say salary will be 11 lakhs in that way. So how would you combine the results? By taking an take average when you have numeric output. Take majority voting or hard voting when your output is, yes, when your output is categorical. Now there is, yeah. Yeah. Yes. Training will change. When I split the data into training and test, are you saying each time I sample randomly and get data, will we get the same data always in training? Randomly I'm sampling. Oh, absolutely. Absolutely. No, no, no. It won't. Maybe you might feel that this observation might be getting trained multiple times, but do you know what? So is the case with the other observations also. All the other observations of first test split might start appearing in training data. That's fine. Okay, this is one part of the story. So now you understand averaging. You also understand voting. Done. Hmm? Now, but what voting did we discuss? Hard voting or majority voting. Okay. Let me put this aside now. Now let's look at the overall accuracy. When I train my model and test it on the test data for all these 2000, for each and every observation, you can calculate whether it is right or wrong prediction, and overall you'll get accuracy. Agree or disagree? You build a model, you test it on this first observation. Okay, predicted value is something that you get. Predicted value is say default. But when you look at the actual value, okay, say actual value also says person will default. It's a right prediction, right? Say you apply this model on the second observation, you take all the inputs, supply to your model, you get the output as the person will not default. But say for this observation, actual value is default. So it is incorrect classification. In this way, for all the 2000, you would get how many are correct, how many are incorrect. So number of times you get the correct results divided by overall will give me what? Accuracy. Okay. I get the overall accuracy now. Agree or disagree, friends? So I get accuracy for base learner 1. For this base learner 1, when I apply, I get accuracy. What is accuracy? Maybe 90%, whatever. Then once again, I split the data into training and test. I train the model. I test it on the test data here. Okay, and I get the overall accuracy for base learner 2. Say we got an accuracy of 88%. Now I try out base learner 3. Say accuracy is 92%. How do I combine the results? By taking an average. Simple. If I take an average, it will be called as simple averaging or what voting? Yes. Now, instead of simple averaging, I can proceed further with weighted averaging also. What do you mean by weighting average? That algorithm which gives me the highest accuracy, I give it the highest weightage. That accuracy which gives me the next highest, slightly it will be given less weightage. This will be given least weightage. Okay, that's how it is calculated. By using some normalization, it is done. That's a simple calculation. Okay. Next time I'm missing anything else. Okay. There is, sorry. Any question from me? Weighted average means if an algorithm is giving me more result, I'll give it more weightage. If an algorithm is giving me less result, I'll give less weightage. Common sense. Okay. Yeah, Kali, please go ahead.
Initially, when we have the sample data, we are splitting it into train and test data, 80% and 20%. Again, for the
Yes.
Blade Learner 2 model, we are splitting the train data again to train and test.
Not train data that you have into training and test.
Okay, so I got confused because there also we have train and test data, but test data remains the same, right?
Test data, that is one scenario, Kavya,
Okay.
where you allow your test data to remain the same. Scenario 2 is you can let your test data change because we are looking at overall accuracy.
Okay.
We are not looking at every record. We are not looking at what is it that the base learner 1 is predicting for record 1. What is it that the base learner is predicting for record 1? What is it that the base learner 3 is predicting for record 1? That is not what we are bothered about. If that is what you're concerned about, then you need to ensure that the test data remains the same.
Okay.
Since you are interested in overall accuracy, you are allowing your test data also to change. So for third base learner, again from this original data, you split that into training and test.
Yeah. Got it, sir. Yeah. Thank you.
Okay, no problem. Now, okay. I would like to take an example where, say we have a two-class problem, whether a person will default or not default. And say you have three base learners, base learner 1, base learner 2, base learner 3. And base learner 1 predicts that there is probably 70% or 75% probability that a person will default. That means there's 25% probability that person will not default. Then base learner 2 might say that there's only 10% probability that a person will default. That means 90% probability that person will not default. Then base learner 3 comes into picture. Say base learner 3 says that there is 15% probability that person will default, 85% probability that person will not default. Now, how do I apply hard voting on this? And how do I apply soft voting on this? Hard voting means in this, using base learner 1, what will be the result? Default. Okay. Then using base learner 2, what will be the result? Not default. Then using base learner 3, what will be the result? Not default. So overall, what will be the output? Not default. That's the majority. If I apply soft voting, what it does is, it is going to take an average. What is average of these three going to be? Anyone? 0.33, right? Agree? Here, what will be the average? Point 7 approximately, or 0.67 to be precise. Agree? Okay. Now in soft voting, what happens is it will take an average. And which class has the highest probability? Not default. So the final result will be Making sense? That's how hard working and soft working works. Okay. All right. Okay. So we understand the difference between hard working, soft working, simple average, and weighted average. We also now understand bagging. Now, what do you think is the disadvantage of bagging or advantage? Okay, let's discuss about both. What are the advantages of bagging and what are the disadvantages? Think and answer, please. What is the advantage of bagging? Obviously, since it's an ensemble technique, it will help you avoid the, it will help you increase the accuracy. And it will also help you bring in more stability. But what do you think are the disadvantages? Sorry, time consuming. Okay. And interpretation reduces. Interpretability reduces. And yes. And you know what? One other additional advantage is bagging will allow parallel processing. Because one algorithm versus another, there is no relationship. Right? Test data, that's it. But the results of the model that I built, will those be used for the second model? Results of one model is not used for another model. You have training test data. Training data keeps changing, but different algorithms are being built continuously. Algorithm 1, 2, 3, etc. Right? So since all these are different algorithms, you can run those algorithms in parallel. Right? So parallel processing is possible when it comes to bagging. Okay. All right. There is yet another disadvantage with bagging. Think through and let me know. Though we are building different algorithms, though you are splitting the data into training and test, though each time the training data set is different, do you think the training data set will be completely different? You have a data set. You're taking training data, test data. One split, done. Again, you're taking training data, test data. Another split. Again, you're taking training data, test data. Random split. There are 3 different training data sets. Do you think all these 3 training data sets will be completely different? Why will it not be different? It's all from the same data, point 1. Point 2 is, it is sampling with replacement. You're getting the data, but you're replacing the data once again, right? Sampling with replacement. Each time you take every observation, it's from the same lot. And also we discussed about a rule, out of bag rule. What is that rule? Out of bag. What does that rule say? Out of what does that rule say? There's a number. Out of the entire data, how many data points only will be repeated? Repeated. 63.2% of the observations only will be repeated. And remaining 36.8% of the data will not be repeated. So now tell me, how different do you think the training data sets will be? Very, very different, or will there be quite some overlap? There will be overlap. If there is going to be that overlap, do you think there'll be correlation between the different decision tree algorithms that are being built and the rules that decision tree generates? More or less, there'll be overlap between the different decision trees that you're building because there is overlap in the training data. There's overlap in the different training data sets. Hence, the algorithms that you're going to build, which will generate rules, decision tree generate rules, will also be overlapping. This is a disadvantage with bagging. Okay. So the base learners, BLs means base learners, will have correlation. They will be correlated. Since they will be correlated, you need to figure out a better way to handle it. Duplication also will be there. Yeah. That is also. I remove that, but even if it learns twice, that's okay. You leave it. Just leave it. Because anyways, one rule repeating again it doesn't learn it again. So duplicate will be by default ignored, kind of. Okay. So one second. I've just made that flow so that I don't miss out that specific flow. Come on. Come on. Okay. So anyways, I mean, it's taking its own sweet time. All right. So to counter this, we have a technique which is called as random forest. So we are done with bagging, my dear friends. Okay. Bagging is bootstrap aggregating. Usually it is applied to tree-based algorithms. Another thing. You have tree-based algorithms, non-tree-based algorithms. Homogeneous algorithms, heterogeneous algorithms. Homogeneous means you use the same algorithm. Heterogeneous means you use different algorithms. Within homogeneous, if you're only going to use tree-based algorithms, like decision tree, only decision tree, then it's called as tree-based algorithms. But within homogeneous, you can also use non-tree-based algorithms, only KNN, for example. That is non-tree-based algorithm. Okay, let me give you a high-level indication here. So you'll have homogeneous algorithms, heterogeneous. Within homogeneous, you can have tree-based or non-tree-based. Tree-based example would be decision tree. Non-tree-based example would be KNN. Any algorithm which is not tree-based. Okay. We have generative, non-generative. Within generative, you have boosting, of course, bagging. Bagging is something which is debatable, friends. But still, based on the very logic which our friend was talking about, that fine, you're saying that different algorithms are different, but then the test data is still the same. When you build algorithm 1, you'll have train and test data, right? Going by your logic, what you told. So the test data would remain the same from the first algorithm. In the second algorithm, you are making use of the first algorithm's test data only. In the third algorithm also, you are making use of the first algorithm's test data only. So from that standpoint, it is also categorized as generative. Okay. And then you have random forest. In non-generative, what do we have? Voting and stacking. Within voting, we have hard voting and soft voting. Soft voting is averaging. Within averaging, you have simple averaging and weighted averaging techniques. Okay, at a high level, this is how it works. Okay. Okay. And then we spoke about bagging. And what is one disadvantage of bagging? The trees or the base learners will be correlated, because quite a few observations will be overlapping from one model to another. To make it uncorrelated, people came up with something called as random forest. What does this random forest do? When you have a tree and when you split it, at each split, random forest is going to randomly select only a few features. Features means what? Columns, inputs, variables, right? So it is going to select at every split, not all. So if you have x1, x2, x3, x4, x5, x6, x7, x8, x9, say you have 9 inputs and say you have 1 output. Then each time it splits, it is not going to select all 9. It will not select all 9, but it is going to randomly select only a few features, or it's going to randomly select only a few inputs. Okay, just to ensure that every tree that is run is uncorrelated. What is a forest? Forest is a collection of trees. So random forest is nothing but collection of decision trees. Forest means it has multiple trees. So forest contains multiple trees. That's it. That's it. Otherwise, it's decision tree only. Otherwise, it's decision tree only. The only thing is within random forest, you say that build multiple decision trees. If you say build 10 decision trees, then for each of these decision trees, when it's trained, at each split, only a small set of these inputs are selected. While there are different rules, the default rule is if your output variable is continuous, then at each split, P by 3, where P equal to number of inputs, would be the number of features which will be selected by default. If you have 9 by 3 is 3. Here we have 9 inputs. So 9 by 3 is 3. So at each split, how many features will be randomly selected from these 9? Now what you're doing is you're trying to ensure that you train your model on different inputs, on different observations also. When you usually split the data and train, only your observations will vary. But here your inputs are also varying. So you're training on different sets individually and then combining the results. So accuracy tend to be higher for random forest. Both ways. You're ensuring that on complete different data sets. Exactly. Absolutely. Okay. And also, this guy who has come up with this random forest also says that minimum node sample size should be equivalent to 5. Meaning, at every node, if you want to split it again further, minimum how many observations do you need? 5 observations. If you have only 3 observations, don't split it because the rule is minimum 5. What is this for? For continuous, that is regression problems. Then when output is categorical, binary or multiple categories, and this problem is called as what problem? Classification problem. Square root of p is suggested. Let me use 36 inputs. It'll be easier, right? If I move on and on, say there are 36 inputs. Okay, if you have 36 inputs, p by 3 will become 36 by 3. So how many inputs will be selected? 12. Okay. Square root of p, what is square root of 36? 6. So 6 inputs will be selected. And the minimum node size suggested by this guy happens to be 1. This is the name of the person who has come up with this particular logic. Oh, no, it is used. Bootstrap sampling only is used. Bootstrap sampling. I'm trying to see if I'm missing out on anything. Just give me a minute. I made huge list of stuff that I've written, but I possibly cannot cover everything. Just give me a minute while I try to get some additional information for you guys. Okay. Okay. Now, can we do parallel processing here when it comes to random forest? Yes, parallel processing is possible because you have different decision trees that you're building. Okay, multiple decision trees, and each decision tree is a different algorithm in its own. So once again, parallel processing is possible when it comes to random forest. Similar to bagging, you can do parallel processing here as well. Okay, so bagging, first we understood about decision tree, then we understood about bagging. Now we are understanding about random forest in a structured manner. Okay. Now let us understand yet another algorithm, which is called as boosting. Let's go ahead with boosting. So bagging is bootstrap aggregating. We discussed about this. Then we spoke about random forest. Within random forest, these are the various hyperparameters. Maximum number of features that should be selected at each node is determined based on square root of p for classification, where p is a number of inputs, p by 3 for regression problem, where p is number of inputs. Number of decision trees that you want to run, number of jobs you want to run, minimum number of sample leaves, so on and so forth, are your hyperparameters. Okay. Yeah, Madhuri, I like you guys asking questions because I will also probably try to answer this because I have made a list of some 112 pages. I'm not able to go to each and every section to tell you guys. So yeah, go ahead, please ask.
Sir, in random forest, you said there will be different decision trees, right?
Oh,
So
yes.
these decision trees are again built with the same rules like entropy, information gain, and the
Exactly. Yes.
root node will be different for all the decision trees.
Root node will be different. Yes, Madhuri, absolutely. You're right. Out of those, if you decide that randomly, if you have 16, not 36 inputs, you decide that randomly I need to select only 6. Out of those 6, information gain is calculated for all those 6, and from that, the one which has the highest information gain will come to the root node.
Yeah, so for categorical, if it is 36 inputs, 6 decision trees will be formed.
No.
Okay.
It is given here. Let me expand that. Yeah, for classification. Oh yeah. Right. You're right. Sorry. Yeah, if there are 36, square root of 36 will be 6. Yeah, for classification, you'll have 6 features.
And also in normal, basic decision tree, we are forming the root node based on information gain.
Correct.
But here that we are
here
not
also information gain only. So out of 36, out of your overall data set 36,
yes.
How many should be selected here? 6 randomly. Right?
Okay. Yeah, now I
Out of these 6, which one will you use for the next split?
which is having high information gain. Yes.
Exactly. The one which has the highest information.
Yes. I got it. Thank you, sir.
Okay. If you have any decimals that you get, for example, sometimes when you take square root of a number or when you divide p by 3, you need not get exact value as 9 or 3 or 6, right? You might get 6.45. Floor values are always selected. Floor means 6. 6.45 will be 6. 5.56 will be 5. So floor values are selected. Decimal part is thrown away. Okay. I think this is good enough for us. So let's proceed further. There are many things like extra trees, which is called as the random forest ensemble with extra trees and things of that kind. Yeah, same Venkatesh. Time consuming, lack of interpretability. These are the two disadvantages. Disadvantages are common because. All right. Now, before moving to boosting, I wish to talk about these sampling techniques. A few are missed out. Simple random sampling technique, you guys are anyways aware of. Then we have stratified sampling. Stratified sampling means you create stratas or groups. For example, if you want to conduct exit poll results, whenever you have elections, there'll be something called as exit poll results, right? And at a national level, which party will win? If you want to do that, what do? Will you go and check every person who has casted the vote? No. You obviously take a sample. Every person who has casted vote would be called as population. Not entire India's population, only people who voted. Everyone who voted would be the population of your interest. From this, when you want to do a sampling, you might say that, you know what, in Uttar Pradesh, the percentage of population is very high. So in my sample also, I'm going to have very high percentage from UP. In Goa, probably the density is less, density of people. So the number of people that you're going to choose for sampling will be less. In that way, you divide. So what are you doing? Every state might be one strata, or every district, right, could be one strata or group. From that, you are going to randomly sample and then proceed further. That's called as stratified sampling. Systematic sampling means usually used in manufacturing. You might say that every fifth circuit board, if you have a circuit manufacturing plant, you might say that every fifth circuit board which is manufactured, I'm going to take it as a sample and I'm going to analyze it, or I'm going to audit that for quality purpose. Or you might say that for the first 1 minute, I'm going to pick up the fifth one. Next 1 minute, I'm going to pick up the fourth one. Next 1 minute, I'll pick up the third. Next 1 minute, second, in that way. Because sometimes what happens is if there are errors in your machines, then maybe every fifth circuit will be defective because the machine gets reset after every four circuits manufactured. Maybe, you don't know. So in that way, you plan, and whatever plan you have, that's called a systematic sampling. These are probability-based sampling techniques. Then you have non-probability sampling, which is judgment-based. Judgment-based means you, based on your rationale, you decide. It's completely dependent on you, on how you want to sample. And in non-probability sampling, sometimes people also do convenience-based sampling. Convenience sampling means if I say go and check with the people who are entering into the shopping mall on what phone they are actually carrying, if I give that. You might prefer a shopping mall which is very close to you. That's called as convenience sampling. But that's okay. That's non-probability sampling. It has its own share of disadvantages. However, it's fine. Okay, those are all non-probability sampling techniques. Bootstrap sampling, anyways, we discussed, right? Sampling with replacement is bootstrap sampling, friends. If you sample without replacement, it is called as jackknife method. Jackknife method means you're not going to replace. That means if I have data, say 100 observations, if I'm going to split that into training and test, if observation number 1 gets selected in training, this is gone. So for the next, you look at 2 to 100. Maybe observation 3 you randomly selected. So 3 is gone from this. Next observation would be selected excluding 1 and 3 because they are already selected. That's called as without replacement. The simple random sampling technique that we have employed is usually jackknife method only. Okay. Then we have cross-validation techniques, in which first thing is holdout method. Holdout method is very simple. The usual things that we are doing. We are splitting the data into training and test. So you're holding out to the test data. Okay. Whenever you have data, when you split that into training and test, you're building a model on which data set? Training data. So test data set is called as holdout data set. You're holding on to it. It's out of your training. You're holding to it. Bagging is a completely different technique, right? Bagging means you build multiple times you split the data in that way. This is not bagging. You just split it once, that's it. Training, test. Test data is called as holdout data set. Okay, k-fold cross-validation we already discussed. If you apply stratified sampling, which we discussed, when you create strata or groups, and then apply k-fold cross-validation, it's called as stratified k-fold cross-validation. Okay. Then we also have leave one out cross-validation. What is leave one out cross-validation? Let's understand. Leave one out. As the name itself says, we are going to leave only one out. Okay. Suppose you have a data set wherein you have 1,000 observations. You have your output variable and say you have your input variables. Leave one out cross validation. What it does is it is going to train your model on 999 observations. Only one is left out. Leave one out. So one observation, sorry, 999. One observation is left out for testing. That will be the first observation. You train one model. Then in the second model, what do? You train on another 999 observations except for two, because second will be in test. Again, you train on 999 observations except for three, and this third will be in test data. Again, you train your model on 999 observations except for four, because this four will be in test data. So ultimately, how many times will you train? 999 times. How many times will you test? Or rather, you train it for 1,000 times and you test it for 1,000 times. Okay. But this is a stretched thing, basically. People nowadays don't use it at all because it will be hugely time-consuming task. And here there is a chance of overfitting, because same observations, multiple times you're training more than what is needed. Okay. Not accuracy. This is a way of testing only, right? The only thing that you're doing is testing. Accuracy depends on how you're using your algorithms, what hyperparameters you use. This is just on what data you're testing. This doesn't determine accuracy. Okay. All right. Now we have something called as boosting. While within boosting, we have a lot of algorithms. Today, people are using extreme gradient boosting only. They are not using any other algorithm today. Okay. And a lot of competitions which are won because people started using extreme gradient boosting. But to understand extreme gradient boosting, we need to understand AdaBoost. Okay. And then we need to understand gradient boosting. And then we will get into extreme gradient boosting. Okay. After that, I think we'll be left with only one thing, which is called as stacking. Stacking is a heterogeneous technique, right? And this is also generative. The previous algorithms will depend, the next set of algorithms will depend on previous algorithms. Okay. So we will probably, understand about boosting after a break. So let me stop this.